Hello, I'm Ishwar Nayak. We are from Group 40. Our topic for the video assignment is ARM C1 Nano processor features. And this is our presentation agenda. I will be covering the first part of our presentation, which mainly includes the introduction, C1 CPU family, the ISA, the load store architecture, and its risk principles. Now, what is ARM C1 Nano? It was introduced in September 2025. It is the world's first ARM version 9.3, a little class core, a part of ARM's C Lumix compute subscription platform. It directly replaces the Cortex A520. Now, the purpose of the chip is it is always on and the ultra efficient computing. It is designed for activation by voice, ambient sensing, and lightweight AI interference. Tasks that run continuously at very low power. That is exactly what the C1 Nano is built for. And the target devices are smartphones, wearables, earbuds, IoT sensors, anything battery powered that needs persistent compute. And the numbers back this up. It delivers a 26% improvement in power efficiency, a 10% performance gain in fetch bound workloads, and it's actually 2% smaller in core area compared to Cortex A520. So more efficient, slightly faster, smaller, and it's a now let's look at the C1 CPU family. ARM's C1 lineup has four tiers. At the top, we have C1 Ultra, the flagship big core, built for peak single and multi-threaded performance. Then the C1 Premium for sustained performance and background AI. And next is the C1 Pro for balanced mainstream workloads. And at the bottom, we have C1 Nano, the most power efficient core in the family. What connects all of these is the C1 DSU, the Dynamic IQ Shared Unit. It manages coherency, shared L3 cache, SME2 unit up to 14 cores per cluster, and all these four tiers share the same ARM version 9.3 A ISA for binary compatibility. Now the instruction set architecture. The C1 Nano runs ART64 only. There's no 32-bit support. This is a fully 64-bit core. All the instructions have a fixed 32-bit encoding, which is a classic RISC principle. Uniform decode and simple hardware. It also follows a load store architecture. Only the LDR and STR instructions can touch memory. All arithmetic happens between registers. This keeps the pipeline clean and predictable. Now, there are four key extensions. SVE2, the scalable vector extension tool. It it has vector length not which is not fixed and has minimum 128 bit and one scales with hardware. And it also covers media and signal processing and AI. Next, we have MTE, memory tagging extension, with 4-bit tags on every 16-bit byte memory granule. It also catches buffer overflow and use after free at hardware level. Next, we have SME2, Scalable Matrix Extension 2, Cluster Shared Matrix Accelerator. It has ZA tile registers. And, and next, we have PAC plus BTI, Pointer Authentication and Branch Target Identification. Provides control flow integrity against common exploit techniques. The processor has four extension levels. At the top is EL3, the secure monitor, the highest privilege level. This is the only entry point between the normal world and the secure world in trust zone. Below that is EL2, the hypervisor. It manages virtual machines, and secure EL2 is also supported, meaning even the secure world itself can be virtualized. EL1 is where OS kernel lives. It configures the MMU, handles interrupts, manages device drivers. And at the bottom, we have EL0, unprivileged user applications. They can't directly access system registers or I/O. Anytime they need OS services, that they trigger an exception and go up the ladder. This hierarchy is fundamental to both security and system design. Now let's look at the register file and addressing modes. In ART64, we have 31 general purpose registers, X0 through X30. The W registers are just 32-bit lower halves of the same registers. X30 serves as the link register, storing the return address for function calls. Each exception level has its own dedicated stack pointer. The PC is not directly writable. For AI and vector work, we have got 32 scalable Z registers from SVE2, and the P state flags negative, zero, carry, overflow work exactly as you'd expect from your computer organization. On addressing modes, the ISA supports all six: base register, base plus immediate offset, base plus register offset, PC relative for branches, pre-index, where the base updates before the access, and the post index, where it updates after.
Hello everyone, I am T. Revant Reddy and I will be discussing about the pipeline architecture and memory system of the C1 nano processor. C1 nano processor uses the in-order superscalar pipeline. And what exactly does in-order execution means? In-order execution means that instructions were fetched, decoded and completed in the sequence they appear in the program. No dynamic reordering has happened and it has simpler hardware and lower power consumption, which is ideal for the background task this core handles. And superscalar means that multiple independent instructions can be issued per clock cycle across multiple parallel execution units. Due to this, instruction level parallelism happens without out of order hardware requirement. And why exactly C1 Nano uses the in order execution? As out of order requires reorder buffer, reservation stations, and register rename and these hardware structures consume large area and power, which is incompatible with C1 Nano's 2% area target. And larger cores such as C1 Ultra use out of order for peak throughput, but C1 Nano compensates with enhanced prediction and forwarding instead. The C1 Nano processor uses the decoupled predict or fetch pipeline. If we use the coupled predict, we face some issues, such as if the fetch stalls, the predictor also stalls. To prevent this, the C1 nanoprocessor uses the decoupled predict or fetch pipeline. In this, the predictor runs ahead independently, filling the queue, and the fetch drains the queue at its own pace, so no coupling happens. And why does this matter for the C1 nano? As the OS and background code is heavily bands dominated, such as dispatch tables, conditionals, and loop controls. And in a coupled design, any fetch stall propagates to the predictor, stalling both of them. So the decoupled design observes fetch stalls in the queue, so that predictor keeps producing predictions uninterruptedly. Now we will discuss about the branch prediction and data forwarding in the C1 nano processor. The C1 nano processor has enhanced branch prediction and it has higher accuracy, improved L1 instruction cache utilization, ideal clock gating on the predictor. Due to the better accuracy, there are fewer pipeline flushes on the misprediction, and it has more number of correct instruction fetched, which increases the instruction cache hit rate. And due to the ideal gating, the predictor clock was cut when the pipeline is stalled, and the power is saved. And now we will discuss about the additional forwarding in the C1 nano processor. The C1 nano processor has additional forwarding ports in the vector unit for the AA workloads. Without the additional forwarding, we face raw hazards as shown in the slide. So, the C1 nano processor uses the additional forwarding to prevent this. The EX output of the instruction 1 write directly back to the EX input of the instruction 2 so that no stall is occurred. This way, the C1 nano processor reduces the raw hazard problems with the help of additional forwarding. Now, we will discuss about the memory system in the C1 nano processor. First, we will discuss about the L1 cache. The L1 cache has two parts in it, that are L1 instruction cache and L1 data cache. First, we will discuss about the L1 instruction cache. The size of the L1 instruction cache is 32 KB or 64 KB, and it is 4-way set associative. And the line size of the L1 instruction cache is 64 bytes, and it is separate from the data cache. So there are no instruction or data conflicts, and it has benefits from the decoupled predictor as we discussed before. And coming to the L1 data cache, the size of the L1 data cache is also 32 KB or 64 KB, and it is also 4-way set associative. And the line size of the L1 data cache is also 64 bytes, and it supports both loads and stores. And it includes an internal exclusive monitor. And what does internal exclusive monitor means? The internal exclusive monitor has two things in it. One is LDXR and STXR. LDXR means load exclusive. Loads a value and marks the address as exclusively held by this core. And STXR, store exclusive, stores only if the monitor still holds exclusivity. Return 0 if it is success or 1 if you need to retry. This provides atomic read modify write without a heavy weight bus load, which is critical for the multi-core correctness. Now we will discuss about L2 gates, TLV, C1 DSU and RAM traffic. First, coming to L2 cache. The size of the L2 cache is 128 or 256 or 512 KB, and it is configurable. And it is 8-way set associative, and the line size is 64 bytes. And it has higher associativity than L1 and reduces the conflict misses on larger working sets. And now coming to the L2 TLB or address translation. This catches virtual to physical address mappings, reduces penalty of L1 TLB misses, and it also helps in avoiding full page table work. And it is also integrated into C1 DSU for cluster level translation coverage. And now coming to the C1 DSU shared L3 and RAM. It manages shared L3 across all cluster cores. It catches coherency via directory-based protocol. And the DRAM access are orders of magnitude and are more costly than L1 hits. And the C1 nano processor reduces the DRAM traffic. On average, it reduces 21% of the DRAM traffic, and at its best, it can reduce the 39% of the DRAM traffic.
Hello, I am Sriram Satvik. Now I'll speak about the topics power architecture, AI acceleration, security and debug features followed by the complete summary. Power efficiency is where the C1 Nano stands out, offering 26% better efficiency than Cortex A520, meaning more work per joule. This is achieved through four key methods. Method 1. Advanced clock gating. In this mechanism, the CPU reduces power by cutting the clock signal to idle units, minimizing switching activity. It aggressively gates unused components such as the vector unit when SME2 is idle. Method 2. Reduced memory traffic. In this mechanism, a smarter prefetch system reduces L3 and DRAM accesses by 21% on average, lowering power consumption in the memory subsystem. Method 3. Improved branch prediction. In this mechanism, a better branch prediction is employed which reduces mispredictions, avoiding wasted cycles and unnecessary power usage. Method 4. Decoupled pipeline. In this, the pipeline units are separated, which improves instruction flow, reducing stalls and increasing efficiency. Area efficiency. The C1 Nano delivers 5.5% higher performance than Cortex A520 while using just 2% less core area, resulting in better performance and efficiency in a slightly smaller chip. The C1 Nano's most forward-looking feature is its AI acceleration capability, notable for an efficiency class core. It includes two key extensions, SVE2, Scalable Vector Extension 2. SVE2 improves on Neon by allowing variable vector lengths defined by hardware, ensuring code portability across different implementations. It also adds support for cryptography, string processing, integer operations, and gather scatter memory access. SME2 Scalable Matrix Extension 2. SME2 enables efficient matrix computations crucial for neural networks. It introduces ZA tile registers, 2D matrix accumulators that allow multiple matrix operations like GEM without frequent memory access. Additional SME2 features. ZA registers store multiple matrix tiles for parallel accumulation. Streaming SVE mode enables continuous data flow from memory, allowing processing for large tensors without manual management. Let us now talk about a few AI performance numbers of this processor. ARM's documentation for the C1 family with SME2 enabled reports the following performance improvements compared to prior generation clusters without SME2. Up to 5x faster AI interference on generative speech, computer vision and classical ML models. Speech recognition. Approximately 4.7 times lower latency. ARM's documented example shows 1495 milliseconds reduced to 315 milliseconds. LLM token encoding. Approximately 4.7 times higher throughput. Up to 3 times better energy efficiency for AI tasks. For the C1 Nano specifically, the shared SME2 unit means that even this little efficiency core can contribute to on-device AI inferencing, handling always-on tasks like wake word detection, ambient sound classification, and sensor fusion at microwatt to milliwatt power levels, without waking the larger C1 Ultra or C1 Pro cores. Now, let us talk about security architecture. The C1 Nano has a strong documented security posture. For always-on core handling sensitive data such as voice, biometrics, health sensors, this is essential. Trust zone is a full hardware enforced separation between a secure world and a normal world. Secure EL2 is also supported, thus enabling virtualization within the secure world. Pointer authentication cryptographically signs return addresses to prevent return-oriented programming attacks using PACIA-PACIB instruction families. Branch target identification enforces that indirect branches can only land on explicitly marked target instructions, defending against spectral-like exploits. Memory tagging extension tags pointers and memory regions to detect use after free and buffer overflow bugs at runtime. Widely deployed in Android 16 Plus for system processes. A processor must be testable and debuggable to be reliable in production. The C1 Nano includes a complete debug and test subsystem. The following are the ones. Embedded Trace Macro Cell (ETM). This records instruction execution flow in real time with minimal overhead and useful for debugging time-sensitive issues. Trace Buffer Extension (TRBE). This stores trace data directly in system memory, removing the need for external debug hardware. Performance Monitoring Unit (PMU). This provides hardware counters to track events like instruction count, cache hits, cache misses, branch accuracy, and pipeline stalls for performance optimization. ATPG and MBIST. ATPG detects logic faults during manufacturing, while MBIST tests on-chip memory by writing and verifying known patterns. This slide displays a summary of all the topics that have been spoken till now. We have tried to keep the content aligned to the course structure. However, we have learnt about many new features which are outside our domain. This slide displays a connection between the topics spoken till now and the topics which we learnt in our course. This project has helped us bridge our theoretical knowledge with the practical solutions implemented in the industry. Hence, it was useful to us. All the content discussed above has been extracted from the official documentations provided by ARM. Thank you.